All right, we are doing the or the geometry review for test on transformations and symmetry. So hopefully you have this packet out so we can get started. All right, number one, ask you to find the indicated angle measure. So A is asking you for what is the sum of the interior angles of a nonagon. So your formula, n minus 2 times 180. Plug in, your nonagon has 9 sides. So that's 9 minus 2 times 180. You plug that in on your calculator, and you get 1,260 degrees. Next one, we have the sum of the interior angles of a quadrilateral. Well, we should know that this is 360 from our quadrilaterals unit, but let's do the math to show that. So we have our n minus 2 times 180. Our n is 4 in this case because a quadrilateral has 4 sides. So then that gives you 2 times 180, which does in fact give you 360 degrees. C and D are your easy ones. The sum of exterior angles, no matter how many sides you have. The sum of the exterior is always 360 degrees. So C and D, both 360. Just to make sure everyone's aware, dodecagon is a 12-side figure. All right, so E, what is the measure of one interior angle of an octagon? You could use your formula, which we take your sum and divide it by n, in which case n would be 8. Or you know that exterior and an interior always have to add up to 180. So I would say, easier way, find your exterior angle first. So 360 divided by 8, so that means that your exterior angle would be 45 degrees. Well then, to get the interior, do 180 minus the 45, you get 135 degrees. All right, next one, we have the interior angle of a 14-gon. Do the same thing, 360 divided by 14. 360 divided by 14, and you get 25.7. And again, that's your exterior. So do 180 minus your 25.7 to give you 154.3 degrees for your interior. All right, one exterior angle of a decagon. A decagon is a 10-sided figure. So this is simply 360 divided by 10. So one exterior angle of a decagon is 36 degrees. All right, the measure of one exterior angle of an 11-gon. We'll do the exact same thing we've been doing. 360 divided by 11. That means that our exterior angle would be 32.7 degrees. And there you have all of number one. Number two, find the number of sides of a regular polygon if the measure of one exterior angle is 24 degrees. Well, to get the exterior angle, we had to do 360 divided by the number of sides. If we wanted to get the number of sides, just do 360 divided by the angle. So we get that we have 15 sides. All right, so to find the measure of, or we have the measure of one exterior angle is 156. Find the number of sides. Well, to find the one interior angle, we found the exterior angle using the sides, and then we subtract it from 180. Well, work backwards. You know the interior and the exterior have to add up to 180. So to find the exterior, do 180 minus the interior, which is, so you get 24 as your exterior angle, and then 360 divided by your exterior angle will give you the number of sides. So again, we have 15 sides. All right, so solving for x. This time we have to figure out what are all these angles have to add up to. We have 6 sides, so we plug it into our formula, n minus 2 times 180. So this is 4 times 180, which is 720. So we know all 6 angles have to add up to 720. So 720 plus equals the 160 plus 80 plus 80, because we know these two are congruent, plus 150 plus 140 plus x. Well, if I add up all those numbers together, I get that is 610 plus x, and then subtract, I get x is 110 degrees. So figure out what my angle what all my interior angles add up to first. Then I add up all those inside angles that I have and subtract from what it needs to add up to get my remaining one. Okay. Number 4, the sum of the measures of the interior angles of a quadrilateral. Well, again, this is quadrilateral has 4 sides. So 4 minus 2 times 180. This would be 2 times 180, which is 360 degrees. The measure of each interior angle of a regular hexagon. Hexagon's a 6-sided figure, so find the exterior first. So each exterior angle is 60 degrees, and then 180 minus that exterior gives us the 120 degrees for each interior angle. Number 6, the measure of each exterior angle of a regular octagon. Octagon is 8 sides, so 360 divided by 8. And we get 45. All right, so the number of sides of a regular polygon where each exterior angle is 144. So we do 180 minus 144, figure out what each exterior angle is. So we know each exterior angle is 36 degrees. So then, to figure out the number of sides, take 360, because all your exteriors have to add to 360. Divide by 36, the measure of each exterior. And you get that it has to be a 10-sided figure. Now we are done with the first page, so flip it over. A floor tile is designed with a regular polygon in the center, with its sides extended. What's the value of x? Well, first, we know it's x is an exterior, so we're going to do 360 divided by n. But what is n? Let's look at that. 1, 2, 3, 4, 5, 6. We have a hexagon, so this is going to be 360 divided by 6. So each exterior angle would be 60 degrees. All right, if the interior angle of a regular polygon is 175, how many sides does it have? Okay, find the exterior. 180 minus 175. So we know each exterior angle is 5 degrees. So then to figure out your number of sides, 360 divided by your exterior angles, the number of them. So you get a 72-sided figure. All right. So we have the design for a quilt piece is made up of 8 congruent parallelograms. What's the measure of angle 1? Well, let's see here. We know that all of these pieces is congruent, so we know all those are going to be the same. So do 360 divided by 8. So this one's going to be 45. Then we got to flash back to the quadrilaterals unit. We know the consecutive angles have to be supplementary. So to get angle 1, subtract the 45. And we get J. All right. Shape below is a regular hexagon. What is the length of its diagonal? Regular means that we know all of our sides and all of our angles have to be congruent. Well, so let's figure out what angle D is. Angle D would be 360 divided by 6, which is 60, but then we have to subtract that from 180. All right, so this angle right here is 120 degrees. So if I draw my altitude in here, my perpendicular line, I now have a 30, 60, 90 triangle. One of my special rights from a long time ago. I'm going to redraw that triangle out. So I can set this up using my tic-tac-toe board from long ago. 30, 60, 90, 1, root 3, 2. I know my 90 degrees is a 6. I want the side opposite my 60 degrees. So I have the square root of 3 over x equals 2 over 6. Cross multiply. So I get that this little piece here is 3 root 3. But look, I have 2 of them. So my final answer would be 6 root 3 feet. All right, number 12. All right, I have 2 adjacent figures are a regular hexagon and a regular octagon. What is the measure of PQR? Well, we know that this whole part right here would have to add up to 360. So what I'm going to do is I'm going to figure out what is this part and what is this part. So my interior of a hexagon, 360 divided by 6 is 60, and then subtract that from 180. So I know this angle right here is 120. My regular octagon, 60 divided by 8 is 45. Subtract that from 180. And this piece here is 135 degrees. So then I know that my angle would have to be 360. Okay. Sorry about that. 360 minus 120 minus 135. So that is so it means that angle is 105 degrees. So measure of angle PQR is 105 degrees. And then we can go on to the next page. Tessellations. All right, so we have to label each statement as true or false. All triangles tessellate. That is true because a triangle has to add up to 180 degrees, which evenly divides into 360. All quadrilaterals tessellate. True, because all quadrilaterals have to add up to 360. So as long as you match things up right, and you have one of each angle next to each other, you're good. All hexagons tessellate. That is a false. Only regular hexagons will tessellate. All right. So the next one, explain why a regular hexagon will tessellate, but a regular heptagon will not. Okay. Well, we've done it multiple times. We know that we want to find the interior angles. We know the interior angle of a hexagon is 120 degrees. So if we take 360 and divide it by 120, we get 3. That means we can take 3 hexagons together and it'll tessellate. Because as long as we have a whole number, when we divide what our interior angle measured by 360 was, we are golden. We tessellate. So let's check our heptagon. We haven't done the heptagon interior angle, so let's do it now. 360 divided by 7 to get our exterior angle, which is 51.4. So 180 minus 51.4, you have 128.6 degrees. So that's our interior angle of the heptagon. So if I take that, if I take 360, divide that by 128.6, I get 2.79. Since that is not a whole number, it will not tessellate. We can't take any number of regular heptagons next to each other and form any vertex of 360 degrees. So it does not work. All right, so 14, which figures will tessellate? Well, we know D will because we already said that all triangles will tessellate. So let's check the other ones. Let's check our angles. Well, this one we have a hexagon. So we know a hexagon, its interior angle is 120. 360 divided by 120, we get a whole number 3. So the hexagon will tessellate. Let's check our pentagon. We get that each exterior angle is 72, which makes our interior angle 108. 360 divided by 108 gives us 3.3 repeating, which means the pentagon will not tessellate. We know the octagon, we just did this one, the interior is 135. 360 divided by 135 gives us 2.6. The decimal, it will not tessellate. All right, to make a tessellation with the figure. Well, we know that the triangle will tessellate with itself. So I'm just going to draw my triangles. There, I made a tessellation with my figure. All right, to find the value of x, I know that at a single vertex, all these have to add up to 360. So 360 equals x plus 20 plus 3x minus 10 plus 2x plus 3x minus 10. If I combine all my like terms, I get 9x. Get 9x, divide by 9. I get that x is 40. Perfect. All right. Number 18, which figures will tessellate? Well, I know any triangle will tessellate. I know any quadrilateral will tessellate. And as we showed in number 15, the octagon will not tessellate. So everything but that octagon tessellates. 18, they had you looking at it in pictures. 19, they've got it in words. So which individual figures will tessellate the plane? Triangle, any triangle will. So we look for anything that says triangle. Any quadrilateral will, so our parallelogram does. Our trapezoid, our square. And the other one that will always tessellate is our regular hexagon. So there we go. There are all of our tessellations. Last tessellation problem. Circle two figures that will tessellate the plane together. We have to figure out, so we're looking for, so let's see. We're going to look at the interior angle measures of the ones that are regular. So our pentagon is 108. Our octagon is 135. This triangle here we can turn into a square. This triangle would turn into a rectangle. So let's look at our octagon. If I put a square right here, then I know this is 90. Okay, so we know that the square and the octagon can tessellate because if we take two octagons together, if I have this over here, I know this angle also is 135, and two 135s and a 90, they make 360. And with tessellations, we're always hunting down that 360. So those are the only ones that will always tessellate together with what we've got. Okay, an isomorphic transformation is a transformation where the preimage is congruent to the image. And other transformations, or ones that are isomorphic, are reflections, because they don't change size. Our rotations, again, they don't change the size, they just change the orientation. And our translations. All right. Symmetry. Which of the following letters have point symmetry? Remember, this is our exactly 180-degree turns. If I rotate the A around, it's never going to look in that exact same orientation. In fact, that's true for most of my letters, except for H, I, O, and S, depending on how you draw it. All right, my angle of rotational symmetry of an octagon. This one, since we're rotating around a circle, 360 divided by your number of sides. So your angle of rotational symmetry is 45 degrees. Find your angle of rotational symmetry of an equilateral triangle. 360 divided by 3. 120 degrees. A composition of reflections in two blank lines is a translation. And this would be two parallel lines. All right, then we get to some actual rotations, reflections, translations, and dilations. All right, we are always starting with these points. A is 5, 9, B is 9, 1, C is 1, 1. If I reflect it over the x-axis, just so you know, this is the same thing as saying y equals 0. That is this line right here. If I want to reflect it, so C needs to be, since it's 1 above, C needs to be 1 below. So that is the point 1, negative 1. Since B is 1 above, B needs to be 1 below. So this is 9, negative 1. Since A is 9 above, A needs to be 9 below. So this is 5, negative 9. All right, a 180-degree clockwise rotation. Around this point, if I rotate this whole figure 180 degrees, C ends up at the point negative 1, negative 1. B ends up at the point negative 8. Oh, gosh. For the point negative 9, negative 1. Remember, for those of my class, we take the x and y, we just make the x and y both pieces negative. So the A ends up at negative 5, negative 9. If I want to translate it 1 unit, or 2 units left and 1 unit up, so 2 units left, 1 unit up, make my new point be 310. I'm subtracting 2 from my x. So I take x minus 2 and then y plus 1. So B would be 7, 2. C would be negative 1, 2. Let's check it. 2 units left, 1 unit up. Perfect. 2 units left, 1 unit up. Dilation centered at 0, 0 with a dilation factor of 3. Multiply every piece of your coordinate by 3. So 5, 9 times 3 becomes 15, 27. 9, 1 becomes 27, 3. 1, 1 becomes 3, 3. Number 27. You're given triangle ABC with vertices -3, 5, 8, 10, and C is -10, -4. The image of AB is a triangle A prime, B prime, C prime with coordinates A prime 5, -3, B prime 10, 8, and C prime -4, -10. So I look at the A. Well, what happened? I went from X, Y, and I did whatever. I got -X, or -Y, -X, and that's true. Or, excuse me, not negative. I got YX, and that's true for each of my points. So that would be a reflection across the line y equals x, because I'm just flipping my x and my y. I'm just changing them around, saying that y equals x. All right, so I have a transformation here. I started here, I ended up here. Well, that would be a reflection because my orientation changed. And that would be across the line, either the x-axis, or you could write it as y equals 0, because if you look, D, here's D prime, we're 2 units away, so here's that middle line. Number 29. Well, that's another reflection because my orientation changed. Here, I am 1, 2, 3, 4 units away, so that means my line of reflection was 2 in the middle. So that is a reflection across the line x equals -1. On a horizontal line, I know I have to be an x equals. All right, so let's see what we got here. I went from -3, 5 to +3, 5. And look at this on the chart. I started up here, and I flipped over, I went over to here. That is a reflection because I started with x, y, and I ended up at -x, +y. Well, that would be the line with the y-axis, or you could write it as x equals 0. Either one. 31. All right, let's see how we changed it. We went from -3 to -4 and 5 to 2. Well, it's not going to be a rotation because our numbers change. I think it's going to be a translation. Let's see if everything fits that. From -3 to -4, we had to go left 1, which was -1. And from 5 to 3, we had to go down 3, which is -3. From 8 to 7, we had to go left 1. 10 to 7, we had to go down 3. So it's looking like we have a translation of left 1, down 3. All right. So let's see. We started out at -3, 5, 8, 10, and then -10, -4. So if I started off with x, y, well, what I have here is I flip my points, took the negative. So y -x is a rotation of 90 degrees clockwise about the point 0, 0. It also could be 270 degrees counterclockwise, whichever one you got. Next one, I went same points. My A is still -3, -5. B is still 8, 10. C is still -10, -4. And then my A prime this time, I have -1.5, 2.5. Well, if I look, my A and my A prime, it looks like I just divided everything in half, or multiplied it by 1/2, 1/2. So that holds true. This one I multiplied by 1/2, multiplied by 1/2. 8 to 4, I multiplied by 1/2. 10 to 5, multiplied by 1/2. So this is a dilation Our dilations are always going to be centered at 0, 0, unless otherwise stated. And our dilation factor would be 1/2. All right, we got some more stuff. We got a reflection about the line y, or x, excuse me, x equals 4. Well, x I know vertical, and here is x equals 4. It goes right through 4 on the x-axis. So, A is 2 units away, so when I reflect it, I go 2 the other way. B is 2 units to the left, so B prime needs to be 2 units to the right. And C is 4 units to the right, so C prime needs to be 4 units to the left. So there's our new figure. All right, 36. Reflect triangle ABC about the line y equals negative x. So that is that line right there. All right, so for line y equals negative x, we take our point xy, and we flip our points and make them both negative. So we would end up at negative y, negative x. So if B is here at 2, 1, then B prime would be here at 1, negative 2. Negative 1, negative 2. All right, so C is at 8, 1. And so C prime is going to be at negative 1, negative 8. And A is at 6, 8. So A prime would be at negative 8, negative 6. There you go. Another way to look at it if we're doing the whole distance away thing. We are 1.5 units away from B, so we need to go 1.5 units for B prime. We are 4.5 from C, so we need to go 4.5 for C prime. All right, another reflection about the line y equals negative 2. This one is horizontal through negative 2. So B is 3 units away, so I need to go 3 below. C is 3 above, so C needs to be 3 below. A is 10 below, or 10 above. Here's A prime at 10 below. All right, rotation of 90 degrees counterclockwise. So I take my xy point, flip them around, and I get negative y, positive x. So B is here. So B is the point 2, 1. So then my B prime becomes negative 1, positive 2. C is 8, 1. So C prime, negative 1, positive 8. A is 6, 8. So A prime is negative 8, 6. So there's my new triangle. Next page, we're getting there. Okay, we find the image of A, B, C after a dilation followed by a translation. Okay. Okay, A is still at 6, 8. B is still at 2, 1. C is still 8, 1. All right, so a dilation of 1/2 means I have to first multiply everything by 1/2. So A prime becomes C 4. 3, 4. B prime becomes 1 and then 0.5. C prime becomes 4 and then 0.5. I'm going to graph also. So 3, 4. Here's A prime. 1.5. There's B prime. And there's C prime. So here's my triangle. Then I'm going to take this and go left 6, down 5. So A double prime. Left 6 means I'm doing x minus 6. Down 5 means y minus 5. So 3 minus 6 is negative 3. 4 minus 5 is negative 1. So A double prime ends up at 3, negative 3, negative 1. There is my A double prime. B double prime, 1 minus 6, negative 5. 0.5 minus 5 is negative 4.5. There's B double prime. C double prime ends up at negative 2, negative 4.5. So there's C double prime, and there we go. All right. Triangle ABC has been reflected over the line y equals negative x. All right. We're only looking for point A. So A is the point 6, 8. If I reflect that over the line y equals negative x, means I flip them around and make them both negative. So A prime ends up at the point negative 8, negative 6. All right, identify the equation of the line of symmetry. Let's see. Looks like your line of symmetry would be right here. So let's see, this is the vertical line, it's going to be x equals. And this is 1, 2, 3, 4. So it's x equals 5. Last page. Identify the first and second transformation so that the image of triangle 1 becomes triangle 2. Okay. Well, I can do this in a couple ways. So this one, we have to translate it and reflect it. The order you go in doesn't really matter. So I'm going to do it twice actually. Translation first, and then the reflection. Okay, so this blue point right here is going to map to this blue point right. It's going to map to this blue point right there. Sorry. So we translate. We have a translation of right right 8 units. So that ends up with us right here. And then we're going to reflect over y equals, the middle of that's going to be half, so we're looking at the line y equals 2.5. Okay, say, Ms. Ragnay, I don't want to translate first. I want to go in alphabetical order and reflect first. Fine, we can do that too. We can reflect over the line. So right here, now we're looking here. We can reflect over the line x equals 0.5, this line right here, in which case we end up here. But then we still have to translate down. Oh, good Lord, we could do a bunch of different things. Erase this. Sorry about that. Change my mind, don't want to erase. So we reflect over the line x equals 1/2. Then we have to translate it. We have to translate down 4 units. Either one works. Two completely different methods, but either one works. All right. I'm sorry for those of you guys who erased and then got really mad at me when I said to not erase. Okay, so draw in all the lines of symmetry if it has any. Well, this little weird shape, the only way we could go is that way. We can fold it horizontally, and that's it. In the next one, we can only go down vertically because we don't have all of our stuff equal. All right, in the diagram below, lines T and R, and actually to the side, are perpendicular. Name the image of FEH after reflection in line R, then a reflection in line T. So I'm going to reflect it in R first. Well, from here, when I reflect it across R, point F becomes point C, point E becomes point D, and then H becomes A. And yes, your order does matter. So then once I reflected one, so then that's my reflection in R. Then I want to reflect it over line T. So I'm taking my CDA, reflecting it over. So point C becomes point P, point D becomes point O, point A becomes point N. So after we reflect it, triangle FEH became triangle PON. All right. What single transformation is the same as two reflections in two perpendicular lines? This is a 180-degree rotation. Last one. Woo! Okay, sorry about that. Going a little bonkers. Determine the number of lines of symmetry, if any, for each figure of polygons that appear to be regular are regular. Well, letter A appears to be regular. And let's see, I can drop one there, I can drop one there, I could go there, I could go there, and I could go there. Remember, if we're a regular figure, our number of lines of symmetry will equal our number of sides. So A has 5. In B, we're not quite regular because our angles aren't all the same. So we only have 1, 2. Circle, we have infinitely many number of lines. There's anywhere you can draw a diameter in. B1. And guess what? We are done. Come in with any questions you might have, and good luck studying.